2026, bringing leaders together for decisions we must fix. March 17 is the day for debate and discussion on the future of precision agriculture. Machines move slowly through them, long roads run, dust in the air and the rising sun. Farmers still read what the seasons say, but the future is calling a different way. Storms come quicker, markets move fast, old certainties fading into the past. We need new signals, we need new sight. We're learning to measure the world with light. From soil conditions to harvest lines, from spectral warnings to data science, the quiet revolution is already here, turning uncertainty into something clear. There's a light on the land showing what must be done, from the first green shoot to the setting sun. We are building systems that help us see, turning photons and data into food security. Optica advancing photonics, A for debate and discussion on the future of precision agriculture. Through drought and pressure, through risk and change, we're designing resilience across the whole value chain. Farmers and engineers standing side by side, writing the next chapter with light as their guide. There's a light on the land and it's leading us on to a world where the fear of shortage is gone, where precision decisions help nations endure, and technology makes the food system more sure. Optica advancing photonics in 2026, lighting the pathway through global supply risks. March 17 is the day for debate and discussion on the future of precision agriculture. So listen for the signal in the wind tonight. The story of farming is changing with light.
Food security is no longer about agriculture. It's becoming a technology race. Climate volatility is rising. Supply chains are fragile, especially now. Quality regulation is tightening. Farming must become more precise, more predictable, more data-driven. Photonics is becoming essential in the field. Optical sensing can spot crop stress much earlier. Spectroscopy enables full-line inspection. Imaging and LiDAR support autonomous systems. But deployment is still hard. Costs must fall. Packaging must survive harsh conditions. Integration must be simpler, and data must be trusted. Today, Optica brings together farmers, photonics companies, system integrators, and research leaders to discuss what must happen next, not in theory, but in real-world deployable systems. If you're building sensing or optical technologies for agriculture and food production, this is the discussion for you. Let's begin.
Thank you very much and welcome. Welcome to the Optica Online Industry Meeting on precision agriculture, farming and food. We're here with a selected group of companies farmers, researchers, and companies developing technology for the next generation of precision agriculture, farming, and food. We have companies, for example, Lumix, providing semiconductor laser diodes. We have research centers like One Planet in the Netherlands, and we have farmers. We're going to have a great 90 minutes of your time trying to find these connections that make this industry flourish. But first of all, I would like to say that I need to thank the people who dedicate their time to the photonics industry and to Optica, especially the people who today are forming the agenda. On one hand, we have integrators. As usual, we have the integrators, the companies that come here with a shopping list, technologies that they need to assemble their plans. Agrina, Ford, One Planet, Metron, and Peltier Institute. And then we have enablers, companies that come with a photonic solution for the companies, the integrators in the room. And today we have Fix from the Netherlands and Grand Farm, all the way from beautiful Fargo, North Dakota. We want to make sure that we make those connections, but the enablers are everyone also in the Zoom room with us. At the same time, I would like to say that we do this for our corporate members, for the Optica corporate members. If you are not yet a corporate member, you want to benefit from having us in your life, optica.org/join corporate. Please join us. This is the best thing you can do to support what we are trying to achieve. And the next time that we all meet together to discuss this particular technology is at the Optica Global Advanced Manufacturing Alliance meeting, which will take place on the 2nd and 3rd of June 2026 in Brussels. If you want to join our industry manufacturing group in which we are talking about how to make semiconductors, optics, micro optics, meta lenses in volume production, come to Brussels on the 2nd and 3rd of June 2026. I would like to also remind that next week we have our Optica Industry Summit at Corning for the manufacturing of advanced optics, and our next online industry meeting is exactly a few days. Quantum sensing and atomic clocks. Join. You want to be a speaker on this event, you want to sponsor, you want to participate, join the website and register as soon as possible. 31st of March is just around the corner. It's crazy how fast 2026 is going. And I also would like to remind before we close the meeting, that this meeting is also live streamed in YouTube. If you are a person that wants to follow from YouTube, if you have any questions for us, please write them in the chat. And if you don't have any question for us, just follow quietly and make sure that you see this message, you see this video live or on demand. And this is also valid for me here with the people in the Zoom room. If you have any questions, if you have any comments, please make sure you post them in the chat, and we will make sure that you voice your own question and you can actually say what you have in mind. And with this, I would like to start now the meeting. Let's start. And the first speaker today, we're going to go all the way to Greece. We're going to go to the beautiful R&D center of Ford, in which Stavros Pisadakis, who is a researcher and also at the same time a farmer himself, he's done a fantastic. Gentlemen, please welcome to the stage, Stavros Pisadakis.
Hello, everybody. I'm Stavros Pisadakis, and today I will make a presentation to you, more or less wearing two hats. The first hat is the hat that I have, for many years now, and this is the one that has to do with my primary, let's say, profession, which is the one of the researcher. And the second hat is that I also have the luck to be the last few years a professional farmer cultivating two family farms under the brand name of Ioannis Pisadakis Estate. So in the same time, I'm more or less a developer and an end user. So very briefly, my base is at Ford at Crete, and I'm the laboratory that we work for many years in the Photonic Materials and Device Laboratory. At the same time, I'm managing two big farms at Chania with more than 2,200 olive trees of different varieties and age, also 110 avocado trees. In any case, both things they have to be done in a professional mode. So this gives me some kind of insight how things can be done and what are the problems that both, different worlds face in order to become, to follow the same path. So the problem is that we need to shift the technologies from the lab to the field. And if somebody goes there, we have the main agro players, which are the farmers, the agronomists, the agro companies, and then we have two a bit more distinct entities, the certification bodies and the governmental organizations that they make the policies. So the question is that if all these players they have the same vision and they understand the necessity of optical fiber sensing technologies at the field. And the second big question is that if scientists and developers, tech developers, understand essentially this, that they have to address and to develop a technology that essentially will have the same time several different end users. So this makes things quite hard. And the problem is that, as everybody knows, precision agriculture relies on precision, and we need precise sensing. And the problem is that the good thing is that photonic technology, they provide precision, the optical fiber sensing technologies, camera technologies, they are quite, let's say, powerful in providing sensing and measurements of quantities that they are not more or less available elsewhere. But we have the main players in the field having different perspectives about the photonic sensing, with scientists having a very, let's say, continuous look on the technology they develop and how this can more or less become better and, a bit more capable in detecting quantities. The farmers, they are sometimes more reluctant in adopting new technologies in the field. And finally, the companies, the big agro companies or smaller agro companies, they do not have a clear picture of how the optical sensors they can enter into their value chains. I give an example here, and the most, let's say, a quick example that somebody can think: a very high-end fertilizer, a quite powerful fertilizer that can be available for a specific crop, and at the same time, this fertilizer to be accompanied by a quite robust photonic sensing technology provided by the same company, the company that manufactures the fertilizer. So it gives a package of two, let's say, products at the same time in order to monitoring the impact of the fertilizer in the field. So the problem is, and the opportunity here from my point of view, is that optical sensing technologies, photonic sensors, they have the power to create the right links between agricultural players. So if you see this kind of AI pictures that, it's quite easy to make them, but they provide a good insight. You have a farmer in the field that more or less uses a photonic sensor, and this photonic sensor is the first link with the field. So the sensor provides fast data, accelerating observation time, and the farmer can get info about his crops in a much more faster mode than usually. The second thing is that this data, they are shared with an agronomist where he evaluates them and he gives feedback to the farmer, but at the same time, the agronomist takes the data and provide them and give them to the agro company with respect to the efficiency of the product they more or less make available in the market. So we see that we have different links between the players, and we see that we have an extended, more or less, chain between them that create a new type of dynamics within the agro-food field. At the same time, we may have certification bodies, or as you can see here, a government person that more or less checks about a specific policy applied. But more or less, the idea is that this type of technologies can generate hot links between the players and enhance trust and transparency, trust between them in order to share data and practices, and transparency to the broader public and the clients that they will benefit from this agricultural product. So at the same time, somebody has to measure, monitor, verify, and certify using these technologies, which creates a new type of landscape that more or less comes to make a revolution in the agricultural field. I will not stay more by means in the specific optical fiber sensing technology that we develop in our lab or we have discussed in the past. But the only thing I would like to briefly to give you one or two examples by means that there can be opportunities for optical fiber sensors in precision agriculture by means of the specific approach of the fiber to the tree, where we can have uh, handy low cost and quite simple in operation optical fiber devices that they can be used in the field. They can be attached on the trunk of the tree. They can be in the tree crown or in the soil to measure quantities that there have not been available until now. I give you two examples here. One is the use of optical fiber sensors for tree grafting, which is a very more or less artisan process that needs some time in order to be evaluated after the grafting uh, implementation. And the second is the use of optical fiber sensors for drone spraying monitoring. This is an example we have recently developed with a Greek company that uses drones for spraying operations in the field, Ionos company. And we had quite, let's say, interesting results with respect to the capabilities that optical fiber sensing technologies can convey into this specific field. So I would like to close more or less and conclude this quick presentation by means of the market story. And the point behind is that who is we do not have a typical market here that we have new technology that somebody will go in a big store with agricultural products and machinery and go off the shelf and buy it, but we have a new landscape that somebody should advocate for these new optical sensing technologies and their capabilities. So somebody can see these technologies as a complement to existing agricultural products and services, which is a new type of opportunity here. And the same time, since we talk about products that they must be quite, let's say, attractive to the end users, that the most of the end users they do not have, let's say, the time to make difficult measurements or the background or the conditions they are not easy, and also the cost is a very significant parameter. Somebody should focus on the willingness to pay by means of controlling the price or the performance of the sensing approach provider uh, to provide unique selling points that they will make all the players within this value chain be more or less happy and give them niche information to each of them in order to continue implementing optical sensing technologies in the field. And the last thing has to do with the simplicity and the type, more or less, of the operation of those technologies. We talk mostly, especially for the optical fiber sensors, that we have technology that must be of low cost, of very simple operation, and quick incubation time, so to give results in very few minutes. And these are similar, more or less, to the COVID diagnostic kits that we recently, a few years ago, used. That you have everything done in 5 minutes in a very simple way and provides you a credible uh, result, a credible measurement. So this is more or less the end of my presentation. I would like to bring to your attention an opportunity here, especially for the European companies in the field. The factory Photon Hub project that is run under the coordination of VUB and provides it's a very powerful tool for developing new photonic technology for end users under a very uh, quite appealing funding scheme are available broadly at the European landscape. So thank you very much for your time and attention. Thank you.
Thank you so much, Stavros. So thank you so much for coming all the way from Greece, and we know like you have this uh, dual side on the scientific side and the farming side. So one of the things that you are saying is totally truth. I mean, it's like what is needed for the adoption of the technology. So when talking about sensing, so one of the things that is always curious, it will be depends on the crop that you are doing what type of sensitivity do you have, or is something that you can have a little bit generic? If we are talking about, like, let's say we are sensing nitrogen, or we are sensing some greenery, or the detecting the what is the health of the soil. So is there like a generic thing and then going to the specific?
We have technologies that they are generic. For instance, one significant point in agriculture is the quality and the characteristics of the soil. So you need soil sensors in order to evaluate the condition of your soil in terms of macronutrients and micronutrients sometimes,
Mm-hmm.
to evaluate the electrical conductivity, the humidity inside the soil, maybe the temperature, etc., etc. So these are standard quantities that most of the farming practices include. Then you shift to specific crops. So, for instance, if you have olive trees or if you have avocado trees, they are two different agricultural practices,
Mm-hmm.
extremely different um, supply chain in terms of fertilizer, different application times. These are two different, let's say, worlds. So you must uh, specialize your sensing tools with respect to the specific crop applied. So this is another challenge and another story that, again, it has specific, let's say, difficulties, challenges to be implemented, but also many opportunities ahead.
Yeah, makes sense. Makes sense. Okay, the other thing is, I would like you to give a little bit of uh, specifications on the sensing that you have in developed, actually, because that's quite interesting. I mean, we know that work, but the public here doesn't know it. So if you can tell us a little bit about the technicity of it.
Can you repeat, please, because the volume is very low?
Oh, sorry. Yeah. So we know that you develop some sensing, okay, and you already put it in your slide. Can you tell us a little bit about the specificity that you have developed?
So, okay, about the specific technologies developed until now in our lab. So,
Yes.
we have developed different types of optical fiber sensors. As I mentioned you before, one is with respect to the detection of spraying drift during drone spraying operations. This is a quite, let's say, that was a quite challenging topic that we developed with a Greek company a few years ago, and we have recently published maybe a year ago at IEEE. And that provided us some powerful alternatives to the existing drift spraying monitoring technologies available using hygrosensitive papers or a bit more complex, let's say, approaches, by means that we can use an optical fiber sensor to detect very
Mm-hmm.
few droplets within 100 square centimeters area, and they have of typical dimension of the order of 20 to 30 to 40 microns. So we have tiny bit of signal that can be detected using optical fibers. The second I saw you was the grafting project. So we implement optical fiber Bragg ratings in the grafting area during the grafting process in order to monitor the efficiency and the success of the grafting. Grafting is a quite empirical. So you need somebody that has a very good background in order to make it and have a success above 50%. So you know this maybe a month afterwards the grafting process. So until then, you are a bit blind. If you have a sensor to know the grafting, especially for sensitive grafting applications, this can increase the grafting efficiency.
Mm-hmm.
We have also other sensors related to the soil sensors that they can measure the pH of the soil or the humidity inside the soil, or we can develop technologies that they can measure gases existing in the field related to the crops, to specific crops, or to specific processes happening in the soil.
Yeah. Yeah. So are the measurement have to be like by taking samples directly, or you can do it standoff?
Depends. Specific measurements, they you can they are three different, let's say, more or less modalities. The first modality is that you have a sensor in the field and you go with a small interrogator and you measure it there. The second modality is you may deploy a network of sensors over the field and you monitor them at either real time or at specific instances. The third modality is that you use a sensor in the field, you leave it on a tree, you stick it in the soil, you collect it few hours, few days afterward, and then you go back in your lab or in your home or in your premises and you measure the sensor there with specific equipment available. So we have different modalities depending on both the quantity we would like to measure and a possible business model that this sensor could be applied.
Mm-hmm. Yeah, absolutely.
Stavros, hello. Thank you very much again for joining. We have a couple of things that I would like to ask you. The first one is, if you could have the ideal spectroscopic sensor for your business, what would be the wavelength range?
A spectroscopic sensor for
Yes, for agriculture. What would be the most interesting wavelength range?
by means of
What
focusing on
wavelengths are you interested in?
okay, depending because mostly the sensors that we work are at the 1.5 microns, which is something that you can find low-cost devices. But if you would like to measure specific quantities like the chlorophyll or more or less stresses in the foliage of the tree, then you have to shift to the visible wavelength. So from 400 to maybe 650, 700. So this, from my point of view, are the two major, more or less, wavelengths that you may deploy your sensing devices.
Fantastic. That allows us to go to all the way to Denmark. Hendrik Sackman from Ibsen. Hendrik, thank you very much for joining. You just heard the wavelength range interesting for Stavros. What business do you do right now in spectroscopic cameras for agriculture?
Hi, Jose. I think you're mentioning two companies in one. So I'm Hendrik from Jabil Optics in Jena, and we are doing spectroscopes, but also, and more relevant here, agricultural camera systems for our customers. Development and testing for autonomous driving, but also for sensing, intelligent agriculture and stuff like that. So pretty interesting to hear this talk. And as you also mentioned Ibsen, I would like to give the stage to Bjarke from Denmark and give him the opportunity to explain what Ibsen is doing in this area.
Bjarke, all the way from Denmark. Are you with us?
Yes, I'm with you. I just posted a comment. I'm not assigned as a speaker here, but what we've done food analysis or spectrometry food analysis for many years. Is actually we are owned by Foss in analytical, so a big player in food analysis, grain, milk, meat, olive oil, and different applications. But our small compact pebble that we've made some years back. I have it here. I sleep with it. And that has caught a lot of interest, and we're ramping this significantly because it fits into handheld devices and multiple probes. So I think this is one of the, especially our VisNIR 500 to 1100 has a lot of applications for measuring different parameters in food, and also the corresponding near infrared version 900 to 1700 also kind of same size. So that's what we see a lot of momentum going right now.
Before I give the floor to Stavros and I ask him how would he use this 900 to 1.1 micron spectroscopic sensor, I would like to know how it works with Jabil. Hendrik, so how does it work? You get that sensor, that grating-based sensor from Ipsen, and you put it on a camera. How is the business of Jabil as a contract manufacturer for the companies in the room?
Well, in case, for example, if we would work with a company who wants to integrate the Epson spectroscope, then yes, this would be this way. So we have then our customer, being a startup or agricultural global player. We have Epson as a contract, as a contractor for the spectroscope, and then we in Jena, we will bring all the bits and pieces together and develop the product for our customer, integrating the spectroscopic solution from Epson. Yeah. Would work like this. So you would reach out to Jabil, and then we bring all the parties together and get the product set up here in Jena, and then transfer to wherever you would like to manufacture it in larger numbers.
Stavros, 900 to 1.1 microns. Is that a wavelength range that we can do something with in the agriculture business?
Yes, because you have I think there you have the hot part of the solar spectrum, and this part of the wavelength band can probably indicate you the stresses occurring in the crop. So this could be maybe an opportunity for developing relevant devices.
Fantastic. Helena, back to you.
Back to me. Okay, so now let's now move all the way to Netherlands, and let's go with Lex Osterveld. So Lex Osterveld is from One Planet IMEC. So Lex, can you please tell us what is coming from One Planet into agriculture and food processing? The floor and the attention is yours. Lex, we cannot hear you.
Yeah, can you hear me now?
Now we can hear you. That was like, what is happening here? Yes. Okay. It's not in
That's
presentation mode.
better.
Now it is. Okay. Perfect. Good.
Okay,
So
and can you
yeah,
see my screen?
I can see your screen, and let us like what is all coming from One Planet, and all the integration photonics into the food manufacturing, please.
Yeah, good day, everybody. My name is Lex Oosterveld. I work for One Planet Research Center. And One Planet Research Center is in the collaboration between two world-leading universities, Wageningen University, who's strong in agriculture, and Radboud University, who's very strong in health and data science. And the third party of this collaboration is IMEC, and IMEC is, of course, a world-leading research institute related to chip technology. And here at One Planet Research Center, we combine chip and digital innovations for a sustainable future in health, environment, and agri-food. And today I want to tell a little bit more about smart food processing. So what we see currently in the food industry, that food process control is based on monitoring limited number of parameters, for instance, temperature, time, pressure, sometimes pH. But for the rest, it relies heavily on extensive offline analysis. So what happens is the product is being made, and at the same time, a lot of samples are being taken, and they go to the laboratory, and then a couple of days later, the results come back. And then after that, the process is adjusted to and optimized. But currently, there is no possibility for real-time process control. And process control consists of two things, I would say. One is feed-forward process control, and that is basically that based on the ingredient composition, you can already adjust your process settings. And the other part is feedback process control. And that means that while the process is running, you basically measure the composition of your product, and you can adapt your process settings. And we think that there's real-time process control based on the information about composition and texture is a huge opportunity for more efficient production of food. So we focus both on composition and texture. For that, we use miniaturized photonic sensors, so based on integrated photonics. And the reason why we do that is because it has a number of advantages. It allows for miniaturization. There is a cost reduction that can be made. There is an increased robustness and reliability and optimized energy consumption. And together with digital intelligence and a user interface, a lot of information can be gained from these sensors. And when you have this miniaturization and cost reduction, that allows for also to put a number of these sensors along your processing line, so it gives a lot of information. So we focus on a couple of different types of photonic sensors. Here you see a number of different types of spectroscopy. So we use Raman spectroscopy, but also UV-Vis, mid-infrared and near-infrared spectroscopy. So basically covering a broad wavelength range depending on what you need. And all these spectroscopy technologies, they have the advantage that, or the principle is that you send light into your product. And because of the composition of your light, basically the light changes in the wavelength range. And when you detect that, it gives information about your composition of your food, for instance, about the chemical bonds which are present. An example of this is Raman spectroscopy. It's a type of spectroscopy which allows really for fingerprinting of chemical bonds in your product. And that can help you to get detailed information of the composition and changes that occur during processing. That allows for real-time process control. And here in this picture, there's an example of where we measured different dairy proteins, an alpha-lactalbumin and a beta-lactoglobulin. And they have different structural features. One has beta sheets and the other one has more alpha helices. And with Raman spectroscopy, you can really distinguish between these types of proteins. So it really helps to get detailed structural information about your food composition. And what we're working on is to reduce the size of this Raman spectroscopy and also to reduce the cost. So current systems cost around 50K. And we think that we can bring it down to, say, around 1,000 euros for when we really miniaturize it and are able to produce it in large quantities. And also we can do elimination of fluorescence background, and we have an increased signal-to-noise ratio. So this tunable laser-based Raman spectroscopy has a lot of advantages compared to commercial, currently available Raman spectroscopy. Another example is mid-infrared spectroscopy. That is basically, we just discussed a different wavelength range. Here you talk between 1,000 and maybe 10,000 nanometers. And also this technology is kind of similar to Raman spectroscopy because it gives information about chemical bonds, but it just gives a little bit different information, which if you can combine it with Raman spectroscopy, it has a lot of advantages. So also here we're looking at to really miniaturize this to chip level. And this is still very in early stages, but we think this has a lot of advantages because it gives very detailed information about your product, and also the sensitivity in the mid-infrared range is usually quite high. Then a third technology that we're working on is laser-based rheology. So what we see for a measurement of texture in a food production plant, that's all done offline, usually with these rotational rheometers, which take quite some time. And there's no really good alternative for real-time monitoring of food texture. And we do that with a laser-based technology, and this allows for the continuous process control. And here you see an example of a dairy product, a quark, which was measured before and after stirring, which gives a relatively small change in the texture. But it's very easy to measure that with this system. Yeah, so these were some examples of new sensing technologies that we're working on, and how will that change your food process? Well, it will result in increased quality because you can better steer your process. It can lead to earlier batch release because you already know the composition during the process and directly after the process. It leads to a reduction of resources that are required because you can optimize the process and there's less waste. So, but also it leads to a reduction of human resources which are required and a reduction of water and energy. But also when you can do feed forward and feedback process control, this allows for less pure ingredients because you can steer the process based on the ingredients and you don't need to have really pure, well-defined ingredients at the start of your process. And it also allows for milder processing because you can really see what happens during your process. So this gives better and faster information, and that allows for well explainable decisions. So this was what I wanted to share with you. Thank you for your attention.
No, thank you so much, Lex. So there are a lot of things happening here. So you are going basically in the full range of the spectroscopy. Sorry, let me. Yeah, thank you for the meeting. So first thing, okay. So what kind of optics do you need when you are doing the miniaturization? Because yeah, what kind of optics do you need? This is like give me a little bit about that.
Oh, I must say that is not my specialism. So what we usually do is we design on-chip tunable lasers. And basically we have kind of a Vignette design which basically means that you have rings which guide the light where you can heat and cool these rings, and that allows you for tuning of the lasers, and then afterwards you basically couple out the light usually with a fiber.
Yeah, so you are going to need the waveguides. That's a little bit okay. So maybe if you don't know that, for the sensing, is it MEMS space?
Is it what do you mean?
Is it the micro electromechanical system? Is it MEMS space? How's your sensing space?
Yeah, the sensor part depends a little bit. It can be CMOS-based sensing or an photodiode, depending on the technology that
Okay.
that we use.
What is your major challenge trying to do the miniaturization?
What for me is the main challenge is that the startup costs for making these chips are quite high, and also the lead times are quite high. So you really need to be able to address big markets to make this work. And that is it takes time to find the right stakeholders to invest in the technology like this.
Yeah, I get. Yeah. So we have here. I mean, in the room. I would like to see. I missed it. Yes. Oh. Tell me a little bit how the photonics industry can help you. What is your requirements?
Yeah, what Yeah, I think in general, what we see is that the photonics industry is not very mature for these more specific types of spectroscopy. So if you go more to the photonics for data, then the photonics industry is well equipped for that. But if you really want to go to different types of spectroscopy, especially in the more exotic wavelength range, that is a challenge. And there we are actively looking for partners that can deliver gain media at these different wavelength ranges.
Yeah, yeah. So let me ask. I see in the room there is Henrik Button for SPO system. So Henrik, can you tell me what is the most challenging things that is happening in this kind of a spectrometers miniaturization that you have encountered with your clients?
Yeah,
He-
as Lex explained, that the upfront cost to start these projects are quite high because you have to invest a lot of NREs to start these projects. So our goal is to lower the entrance level for making some tests and demos, so the customer can decide whether it's a good solution or not before they have to pay a lot of upfront NREs.
Mhm.
So in my perspective, it's the entry cost should be lower, so you can have a screening of both the application, but also the technology platform you're addressing. Because if the entry level is too high, then the rejection to go this direction is too high.
Yeah, that's totally true. And what is and that's between I would like to see have the perspective from Lex and from Henrik, because when you are working with different techniques, you are working with different wavelengths, and that makes us change in the materials, make change in the way that you are doing the wavelength, the waveguides and everything. So how is it coming from going from UV to near infrared, for example? So how is it for you, Lex, and how is it for you, Henrik?
Yeah, for us, the main challenge is then looking for the right gain media. And also, depending on the type of spectroscopy, you really have to select the right wavelength. For instance, for Raman spectroscopy, you have a pumping laser, and you want to select a pumping laser to have an optimum between the signal and the fluorescence, which may be interfering. So and then it's a challenge to find the right gain media. But also you want to have the accurate tuning. So also for that you need to have the right combination of gain media and your chip design.
Yeah. What about you?
Yeah, if I should add, we are working in a hybrid solution, so we're working both on polymer and on glass. So for our perspective to cover a broad wavelength range is that sometimes the polymer is not suited for the wavelengths, either because it has some unfortunate behavior, or for Raman spectroscopy, some polymers have some self-fluorescence effect as well. So yeah, the placement and the choice of material is crucial for us.
Yeah, exactly. Well, thank you so much, and I would like to let's move a little bit about sensing too, and let's go to a company that's called Metron. So they are doing all the integrated photonics for the sensing, and I would like to invite to the floor Michael Allen. So Michael, the floor and the attention is yours. Michael, you You are mute. Michael? Michael, can you hear us?
Yes, I can hear you. You
Oh,
approached
okay.
me. So, Entschuldigung.
No, no, no.
Entschuldigung.
I'm talking about Michael Allen. Sorry.
So it's not me. It's not me. I'm just an observer. I am a farmer, a kid, but I'm also physics.
So
I am
interesting.
very
You say
close to it, but I'm not in the field of agriculture, so I don't want to disturb.
so you're not a farmer.
My dad is a farmer.
Oh, okay. Thank you. Yeah, sorry.
Yeah, my
So
apologies about that. Sorry, guys.
no, it's okay. No worries. It happens. This is the thing that is going to happen when it's live.
Yeah, and for some reason my docking station does not like the second monitor, even though it's turned off. So
And now it's working. Yeah. Now it's
let me go
working. It's
back to the
perfectly good.
beginning here. Yeah, thank you
Yeah.
very much. Michael Allen from Metron Spectra, which is a combination of Metron companies in that work inside of the photonics industry. Innovative photonics solutions for the lasers that they provide into the Raman industry, as well as B&W Tech for their sensor technology and capability that they've developed with spectrometers, both in the near infrared and also in the UV invisible. So a lot of different components that come together. All of these MOEM components are integrated into our Metron laboratory instruments that you may use or have encountered in the past, and these components are also distributed to other players in the industry. So it's pleasure to be a part of the discussion today. I think when it comes to photonics and farming from the viewpoint of Metron and what we see with IPS lasers, the drivers for this industry are really the need for fast measurements, because as a professor of mine said in graduate school, biological samples are very complex and they change very quickly. So from a physics standpoint, looking at different parameters and monitoring them in an entire field or across many acres is both challenging and relevant with respect to time. Obviously, all of the things that we normally do not have in an optical lab, like vibration, dust, everything else that we are doing, we don't have the ability to control for that when we are outside. And we have the need to make decisions very quickly. So I want to talk about just a couple of applications that are on our radar at Metron that may be of interest to you. On the left-hand side, you'll see a standoff Raman measurement of plant moisture and growth characteristics. The spectrum at the bottom of the screen corresponds to the data or the instrumental setup on the left-hand side. This is a concatenated Raman spectrum where we're throwing together the fingerprint region, which has structural information and chemical information about the plant itself, carotenoid, cellulose concentrations, phenylalanine concentrations, and then all the way out to the lower energy side is the stretch regions where you see the OH band. Very similar to the same OH band that you would see in FTIR or even in near infrared as one of the overtones. But Raman is very sensitive to moisture in this case and can give you an idea of both the hydration state of the plant as well as some of the structural and chemical features of the plant, which makes it very interesting to monitor how the plant is ripening and what other information we can take from that. We also have a spectrum with some chemical information from the fingerprint region on the different sections of a kernel of corn. So as you look at different types of plant development from seeds all the way out to full plants, there's a lot of information that you can extract both chemically and in terms of the amount of moisture from the Raman spectrum. One of the topics that was interesting recently has come up and landed on our radar are integrated photonic circuits that can be used for basically moving measurements from the laboratory out to the back of the combine where the field is being plowed and the measurements are actually being made, integrated into the machinery that's used for farming. There's two very unique types of measurements that have already been discussed a little bit today, but near infrared is the ubiquitous technique for moisture, fat, protein. It's routinely monitored using near infrared, especially for commerce and trading in the US. And so we are excited to see how we can position near infrared in this measurement modality, as well as look at Raman for identification, again, getting more high density chemical information from the field. So both of these measurements are well suited for our technologies. Our lasers are very low energy, they're very low weight, very low size, they're small, can very easily be integrated with these chips and basically can help produce the types of data that farmers need to make some relevant decisions about what's happening. One very interesting example of this is the monitoring of sugarcane as well. We're doing a lot of work in Brazil with sugarcane to try to understand how that plant ripens and what we can do to track that process in real time. So in closing, if you look at the evolution of the way things are going and how we can get involved in that, IPS basically is positioned from a laser standpoint to help with the Raman and near infrared absorption measurements that can be made, again, low weight, small size platforms with minimal power consumption. And then the technique of Raman concatenation, stitching together the stretch region and the fingerprint region to give you a lot of information, I think is very, very helpful in this market, as well as integrating all of this together into one single circuit to help miniaturize the technology even further. So that's the end of my presentation. Again, if you have any questions, feel free to reach out to us. We'd be happy to help in any way with your development project, regardless of what stage it's in. Thank you.
Yeah, thank you. Thank you so much, Michael. So first question for me is, you say you don't need that much of the power on the laser. So can you give me a range of what is the power or the energy?
Well, it's not quite capable of running off of a 9-volt battery yet, but certainly powered off of a USB port if necessary. So you're looking at small watts with a few milliamps of power to drive the actual laser itself.
Okay, so and that's tunable lasers.
Tunable? No, these are all fixed wavelength, very
Just
narrow
fixed
line
wavelength.
width.
Okay.
Yeah. Yep.
Okay.
Yep.
Fixed wavelengths. Yeah, absolutely. But about the optics?
From the optics standpoint, a lot of customers obviously like to fiber couple lasers out of the assemblies. We can certainly put these into a TO can. We can put focusing optics on the end of that, or we can put them into a butterfly package with collimating optics as well. So they work in both free space and fiber coupled formats for sure.
Okay, so Stavros, can I ask you, from the point of view as a farmer, what do you think about this technology? Stavros,
I would
you are,
say
yeah.
that it tackles
Stavros.
a very significant problem, that of ripening of crops. And, you know, choosing, let's say, the right time to start the ripening process can essentially save you money by means of the labor cost. It can save you money by means of the production rate. And also, it can also save money by in the extended value chain, especially in the case that you have a cold chain. And for instance, if you have an avocado ripening process, the avocado you must ripen it at a specific point when the fat in the crop is at the maximum rate. If you do it before or after, if you do it later, the fruit tends to become black. If you do it before, you get a lower quality fruit. So choosing the right moment is very significant in order to provide a product at the right quality and at the right price for getting a good profit. So this is a big issue, let's say.
Exactly. Yep.
Yeah. So one of the things that we are having here. Okay, let's start looking. Okay, this is Raman. This is vibrational because that's something that Lex also have. Hyperspectral. I would like to ask Mike Sullivan. So Mike Sullivan from SenseIR. What is your opinion here? And should we go into hyperspectral? Should we don't? Should we stay in Raman?
Well, so we do hyperspectral. We also do hyperspectral Raman, actually.
Mm-hmm.
So basically, instead of getting, one spectra for one point, you're getting many spectra over a whole, 2D field or image, right? So you have a lot more detail where you can say this part of the crop has a certain disease, or this part of the crop needs more fertilizer, and so forth. So it's more detailed. You can fly these on drones or airborne instruments, right? And you basically do a sweep over the field and you can reconstruct this data cube where you have a spectra for every point. So in the agriculture industry, it's been very interesting, right? We sell a lot to researchers. We're still trying to figure out what the general market is for this, who are going to be the industrial buyers and implement this stuff, right? And it is extremely cost sensitive, right? People don't want to pay $200,000 for a instrument, right? They want to sell data. So, people want to spend maybe $10,000, that's a good entry point or something, but it's a very cost sensitive industry at the moment. But we've been trying to, lately we've developed this little guy here that's drone mountable. This is a Veneer instrument that goes 400 to 1,000, and it can be mounted on a drone. We're working with NC State to do drone studies on fields to detect disease and so forth. But something like this costs under $8,000, because we build everything in this. So that's what we're kind of looking into, still trying to figure out how we fit into this whole thing.
Yeah. Any particular challenges that you have?
Oh, I think you have to provide the whole solution, right? We sell to researchers that generate the data, right? But when you mount this thing on a drone, you have a whole new host of problems, like making sure the drone flies straight. You have all these corrections to do to get good data. It's nice to have a nice bright sunlight out there. You take a reference of some white target on the ground and you reference everything to that. So, there can be day-to-day challenges when you're using the sun as your light source. But then there's taking that data and correlating it with disease detection, nitrate, whatever, soil analysis. And those algorithms need to be very robust and, 99% correct.
Yeah, absolutely. This is something that you can connect with Lex, also with Rex, which is going to talk in a moment soon. But I would like, before that, I would like to open the floor to Henry Sackman. He has a question for Michael Allen. So Hendrik, can you please make yourself and say your question?
Hi, sure. The question is, for the spectroscopic systems that you provide, what's the minimum footprint or minimum volume that is possible for such Raman solution? And Michael already ordered, but maybe you can rephrase your answer.
Yeah, sure. It's about the size of two iPhone Pro Max devices stacked on top of each other. Is the easiest way that I can represent it. It's a free space system that rasters. The spectrometer obviously is the largest part of that, and there's an integrated laser as well. So the module itself is a little bit bigger than a couple of deck of playing cards, and has the ability to communicate data and control the laser and do all of that from an external board to the device. So it needs a little bit of care and attention to build something around it, to protect it. But that's the basic size of the device that we're working with right now for Raman.
That's impressive. Thank you for your answer.
Sure.
Thank you. Yeah, and one of the way we are coming back, one of the way to miniaturize is for course using the photonics, the peaks. So who else can tell us about the peaks than Stefan Heinemann? So Stefan, please tell us a little bit how the fixed technology integrated into Metron.
Thank you for the introduction. Very much appreciated. And let me see if you see that in full screen mode.
Not yet.
Sorry, that's about the hotel internet.
Yes, sorry.
But I hope you can see it now?
Yes.
Okay.
Okay, thank you.
Good. Yeah, thanks for having me, Helen. I really appreciate it. And about a year ago, we met in Great Farms, and they really kicked off how we got how photonic integrated circuits and farming needs really can come together. And so I'm happy to be here. Just a very quick summary of what we do is Fix. We are a pure play packaging foundry for integrated photonics and MEMS. So we are in the interface of putting electrical chips and optical chips with the proper software in a small box and make it work. Make it work in 4 different main markets. At the lower bottom, you see the datacom market, CPO market, and we're all here in Los Angeles to address that market, in quantum technology, health, and sensing. So what I'm going to talk about today in one slide, in the next slide, is about remote sensing, whether it's LiDAR or spectroscopy analysis, or how these two worlds actually come together. And that is a thought that was really spurred in the great meeting we had in Great Farms a year ago. We are located in the Netherlands, in Enschede, and since last year, we also have a production facility in the United States in Bozeman, Montana. So let me go to the next slide. This is really a summary on how we see this addressing the needs on how that we heard at that workshop, and that I also heard a couple times today. How can we there's 2 main challenges. One is making the right data available to the farmer in the right format. And the second one is cost it down and make it small and portable so that it can really be used in many different applications. One of the biggest applications that we're working on right now is nitrate and moisture sensing in the field. And to enable that, we need to bring the sensor to a format that is in the iPhone format, and that can be at costs well below $1,000. So what's happening in the realm of photon delta and in the world of Fix is to the upper left, you see a spectrometer on the chip, which is a different approach to what we all know in terms of spectroscopy, going through a grating. This is basically an indium phosphide chip, for example, in this case, addressing the near IR wavelength, and it has a grating structure, and it defines multiple channels. In this case, is 16 channels on the surface of the chip that couple a specific spectroscopy into the indium wavelength range into the spectrometer, and then you use AI to teach the spectrometer to the specific things that you want to observe. Another one is a Raman spectroscopy device, and I find this very interesting. It really fits in the palm, in your finger. It's not larger than your index finger. That is actually a company that was selected last year by Photon Delta to commercialize their technology, and it's now commercially available when you see this at the lower right. So this is, the typical field of spectroscopy and various degrees of automation, miniaturization. We had a great discussion last year and what the farmer really needs, and we heard this also today, is actually two things. You want to have the capability of spectroscopy, but you also need imaging. So there's hyperspectral cameras, obviously sweep the grading or sweep the spectral response in one axis and then the local response in the other axis. Now, there's a very nice new technology around that has a couple of benefits. One is you have actually a CMOS type chip that gives you the imaging, whether it's LiDAR, it can actually do LiDAR, or it can do regular imaging. But then you need the spectral response, and we put the spectral response in the illumination. And we just heard that illumination is very beneficial to take out daylight sensitivity. So here, on the upper right, you see a 3 wavelength integrated light source that can have fixed wavelengths, you can also sweep the wavelengths, and it's made possible or enabled by the PIX technology, where we have ring resonators on a chip. We have a couple of different gain media, and together you get a 3 wavelength sweepable light source. You put that out in the field for the illumination, and then you receive it with the chip that's shown at the lower bottom. So within tens of hertz, you get a full image and spectral resolution of the area of interest. Thank you.
Thank you so much. Thank you so much. And that's actually, yeah, this is the way that we are integrating all the photonics into the devices, that they are going to be deployed, but they have to be also be meaningful for adoption for the farming and also for the food industry. So we have a question from Hendrik Sackman. Hendrik, you are asking to Michael. Could you please? They already did it. Sorry. Mike Sullivan. So it's what is the role of the farming? So Mike, can you? Ivan Drago is asking to Mike. So
Yeah,
Ivan, yes.
I just answered that. So it's I mean, what I like about this application, it's just there's huge issues, right? Everybody eats food. Somebody said we're going to have to produce more food in the next 50 years than we have since the beginning of time or something crazy. And we have challenges like climate and so forth. But the goal of any technology for the farmer is to improve their yields, right? Every seed they plant in the ground, they want to make money off of that. So you can do that through targeting fertilization to reduce those horrendous costs. You can do early disease detection, all sorts of things that would improve the yield for the farmer. So that's the real return on investment.
Yeah, indeed. Stefan was talking. It's like yeah, we need the spectroscopy, but we also need imaging. And someone that is actually very diverse and have been working very close to the farmers is Rex. So Rex is the endowed chair and director for the Pelter Institute for Advanced in Agriculture Technology at North Dakota State University. So Rex, the floor and attention is all yours, because you have two beautiful projects to present here.
Thank you, Helena. I'm going to share my screen here. So thank you. First, thank you, Helena, for your introduction, and thank you, Photonics, about this conference and this invitation. So my name is Rex, and I'm the endowed chair and the director for the Peltier Institute at the North Dakota State University. And today we're going to talk about some of our ongoing research in AI imaging and robotics field in precision ag. So our group is focused how to apply. We do apply the research. So we focus how to using AI and imaging processing and robotics technology. Focus on that real resolutions for the farming applications. So today we're going to talk about the herbicide resistant weed control. That's one of our ongoing projects since 2018. But before that, I will just want to one slide introduce our Peltier Institute. Just last year, we are NDSU, North Dakota State, with a very generous family here in North Dakota, Peltier family, donate a big, significant amount of funding for our university to start this Peltier Institute. And this institute's mission is really want to collaborate in industries like you guys and also other academic and be the leaders for agricultural technologies around the world. So back to the research on the weed control. So I don't have to dig too deep about how the weed control is very important and how we're spraying right now. The dominant method to weed control is still spray the whole field and then using chemicals, right? That have a lot of challenging herbicide. What if that weed is herbicide resistant? It doesn't matter you spray or not. It's also is the environmental impact. We don't want to spray too much chemicals on our planet. And that gives to us opportunities is how can we using this kind of imaging technologies, drones or robotics technology, AI, to help our farmers and help our farming to help them better manage the weed control. So since early 2019, our group is starting using this imaging technologies in both greenhouse and the field, collecting pictures for our AI database. So in 2019, we just test the water. We just got a funding from USDA. So we collect about 2,000 pictures, just test the water. And that went very well. And then starting 2020 until this year is 2026, actually update that. We are collecting multiple species of weed and this crop, both in greenhouse and field. We collected over 20 million pictures. That pictures not only RGB pictures. We're using all kinds of sensors on the market. The RGB pictures, hyperspectral. We tackle 400 nanometers all the way to 1700 matter what. Just the last month, we just got a camera can go to 2500 nanometers. So also we're doing thermal pictures, and we also do LiDAR, and I don't have to mention all this picture. You guys are expert about imaging sensors on this. Using LiDAR, we really trying to focus on the line of the crop and the weed to find that for our autonomous vehicles, for our robots. So on the side, we're also investigating. We are off-the-shelf robot. We bought the robot from robot companies. We also build the robot from scratch. So as you can see, this is the NDSU Summit. We built that robot from scratch. And then that robot, we call it mini weed bot. The function is that robot is we try to collect all the field data of both crop and the weed. And also we try to install a mechanical component in the center. We call that delta arm. You can see that we can find the weed and the mechanical remove the weed with the root together. We're still testing that, and then that's turn down my value. So that's the robot is operating in the field. Right now it's a remote control, but we're trying to install different sensors or LiDAR sensors to detect the role so we can make that autonomously. And we on the side, we also detecting using the spray technology, a target spray. So we built this, we call the weed bot, and then this back in 2019, and we collect the data. We also test this imaging technologies. We using different conditions, the sunlight, shade, or different method, rain or not rain. So all this field conditions to detect the weed, and then the target spray, turn on that nozzle and turn off that nozzle. Another thing is we compare to the industry product is at the NDSU at Peltier Institute, we try to build this all robot technologies with this platforms from scratch. And there's a learning platform for the students. And the second thing is we want to cut the cost. Our target is all this robot is below $5,000. So all that to the farmers can in the end can be able to afford this and also apply this technology on their farm. Of course, we are trying to using drone technologies as well. We fly over the field and then using this automosaic imageries, and then we're using a GIS method and a machine learning method to create a prescription map, and then that prescription map can tell you different colors represent what. Red means weed, and green means crop. In this case, it's sugar beets. We do have another funding project for sugar beets weed control as well. So, and then next, we translate this prescription map to our grid prescription maps, and then we can import this map to a sprayer. If your sprayer can read the prescription map, and then now you can tell the sprayer, tell the nozzles, only spray the red part pattern and then leave the green pattern alone. So in that case, we can adjust the grid size as well. You can to determine your nozzle's precision, how big area you want spray. And then hopefully you using this method can save your herbicide input and also not to mention about the environmental impact. Two ongoing projects based on our USDA project, and then we have got some additional funding opportunities working with industry partners, with companies in the US right now. And then we're trying to using this drone technologies and edge computing using AI with the companies called Botlink and Poly. And we're also collaborating. There's a big NSF grant that we got funded at NDSU. It's called NSF AgTech Engine in North Dakota. And then we're trying to collaborating with the different partners together and on this weed detection using drones in real time. And this time is not farming field. We're trying to tackle the non-farm areas. It's, for example, you can see there's some solar panels there. Maybe it's in the ditch. There's some, the DOT project. The government still need to do the weed control along the road. Maybe that's you can use drones to detect them, and maybe using spray drones to apply that on the side of the road. So we are working on that as well. Another thing is we're working on, this is a very exciting project with the Grand Farm, and the Novo is here at that panel. With North Dakota, we have a very exciting initiative, nonprofit initiative called Grand Farm. And we are, as researchers, we're collaborating with them, and we got another project funded from the North Dakota Department of Agriculture. We're trying to using drone technology to detect the Palmer amaranth. And Palmer amaranth is a very big problem weed, invasive weed in the U.S., probably in the world. I don't know about the Europe side, but in the U.S. side, almost every state have Palmer amaranth. And this is a herbicide-resistant weed. This is bad news for the farmers. It can cost you 7 to 90% yield loss. How can we detect the palmer early enough so we can tell the farmers to react quick? So we are working on this project using drone technology to detect that early stage of palmer and tell the farmers, hey, our AI and the drone technology can tell you have palmer in the field, do something, please. So this is a project we got a very successful first year, and now it's in the second and third year stage. And that's my student Austin. He's working for a big farm machinery company right now. He's standing next to a palmer right there. It can grow over 6 feet tall. So that's a very problematic weed. Beyond of that weed research, our group is also using hyperspectral, doing a soil moisture, soil nutrient. We have a project going on right now, 2 PhD students working on that. We also tackle livestock monitoring using thermal, using near-infrared technology on their, we call it bovine respiratory disease. And then they're coughing and they have a fever, and it's causing a big loss for the ranchers. On the right side, we also do food quality control. Actually, that's how my research group started. We try to using imaging, multispectral, hyperspectral imaging technology on meat product and meat quality, pork, beef tenderness. We also doing lettuce. We doing sunflower seed. We do all kinds of tofu qualities. We do lots of food research using non-destructive, basically imaging technology to detect their food. So the food qualities, the food damage, and insect damage, all that. So I know my time is limited, so that's end of my slide. One more thing is I want to say that is all these fancy technologies have challenges, right? So I do want to point out 4 different challenges that we might face in the future to discuss with you. It's just my opinion. As one is cost. With all this fancy robot and its drones, if that costs $30,000 or $300,000 each for farmers, then we need to rethink how can we lower the cost, lower the sensors. How can we cut that hyperspectral cameras down to that researchers or most important things is farmers can afford. Another thing is technology adoption. We develop this technology. If we cannot develop it as a user-friendly for farmers, as a plug-play system, it's gonna be a hassle because we don't want to give a 20 days training training boot camp for farmers to just to use how to use this sensors. That's not our mission as well. Data management, we generate this one hyperspectral imagery maybe is 1 gigabyte or right, so 500 megabytes. All those data, all this information, how can we find the useful information out of that and can translate that to useful information for the farmers? And the last thing is the policies. How can we make sure that all the policies, all the regulations works for the industry and for the farmers as well. So that's the end of my presentation. I hope this will gives you some insight or some discussion about the discussion point about how AI, robot imaging works in the future farming. And thank you, Helena, again for this amazing discussion point. Thank you.
Yeah, thank you. No, thank you so much. Thanks a lot. And actually, I mean, there are several things that we as a photonic industry we have to be aware of, and it's exactly like what is coming from the farming directly to be adoption, and that was part of the discussion that we have last year that Stephen mentioned. And actually, I want to bring Noel because Noel is part of it. So um, it is in between hyperspectral, multispectral, RBD imaging, but also spectroscopy and miniaturization. I was asking behind to Zach. I don't know, Zach, if you will be able to open your mic, and I would like to get your opinion about this, like because the adoption of miniaturization into the farming machinery coming from big machinery like John Deere is a different perspective. Like if it's going to be a small robot like the ones that you are presenting, Rex. So yeah. So Zach, could you please unmute your mic? Unmute your mic.
Yeah. I
Thank
mean,
you so much. Welcome.
yeah. I mean, you talked about robotics and things like that, and certainly
Yeah.
that's, I would say, kind of a wild card. I mean, obviously they are inevitable, but I don't think that uh, anybody who claims to accurately forecast, how that's going to impact uh, agriculture or claims to know, I think is anyway, I probably wouldn't trust them. I mean, it's going to take some time to unfold, but I think for for the near future, right, it's going to continue to be kind of large scale, large machines, things of that nature. Yes, eventually miniaturization will play a role, and for certain applications, perhaps of spectral sensing, miniaturization will have its benefits, but I don't know, from my perspective, miniaturization is not a huge need right now.
Okay, so Zach, from your perspective, I mean, as a John Deere, because this is one of the things. This is like this is one of the companies that have like heavy machinery for agriculture, but well, for other things too, but and also like in different ambits. So if he's talking about the adoption of the spectral of spectroscopy of the imaging into the machinery, from your perspective, but it's more efficient actually, because when you are making when 2D is making machinery, usually is making it in more generic way. It's very difficult for a business like yours to have a specific machine for a specific crop. It's possible, but the project typically is like more generic. It's for for several types of crops. So what is your perspective also about the imaging and the spectroscopy?
Yeah, that's a really good point. When it comes to any sensor, right, that we would entertain, certainly we want it to work across many different machines and crop types, right? And probably have the ability to sense many different things. So that, yeah, that's very important to us, right? Because even though, we're the largest manufacturer of agricultural equipment, our volumes aren't that big in the grand scheme of things.
Exactly. Yeah. Makes sense. Makes sense. So thank you so much. Thank you so much for giving us your perspective. I would like to do the last place to a very special person, to Noel Anderson. Grand Farm have been our partner in this market of we started with AgriPhotonics last year, and we will continue with it, and it's one of the best partners that we can have in this ambitus. So the place, all the attention is going now to Noel Anderson from Gant Farm. He's a technical advisor. Noel, the floor and attention is all yours.
I'll give a moment for the graphic to show up. And is it showing? Is my slide showing?
Yes, it is.
Okay. Yes. Last year we were able to host the AgriPhotonics conference at Grand Farm, and I gave a presentation entitled Frontiers in AgriPhotonics. And in the minute or two that I have here, I just wanted to provide an update on the three topics that I talked about, as well as add to what Rex had commented on weeding robots, because it seems those are a product of growing importance, and there's some technical challenges there that optics might be able to help with. I haven't heard anyone talk about terahertz sensing this morning, and I guess that's adding to my evidence that the focus on work for terahertz in agriculture continues to be in China. That's not to say that there aren't activities going on in Europe, the US, and elsewhere, but when I go and do my every 3 to 6 month literature update review, most of the papers have Chinese authors. We continue to see advancements in transceivers, and that is a major need, because we need the power to be increased for the signal that's transmitted, and then also greater sensitivity for the signal that's received, either through transmission or reflection from the ag material. A couple weeks ago, I had a patent in the US, or patent application in the US published. That's the number there at the end of the line. And that's able to go into more detail on some of the ag applications of terahertz that I wasn't able to share last year at the presentation. There's been some steady progress with Sentinel plants. Sentinel plant is one that is grown because it is more sensitive to an environmental stress. And Interplant is a company that has been developing both genetics as well as sensing technology, so that when soybeans have stress from white mold, they fluoresce, and then that fluorescence can be detected. So rather than sending a human out to walk the field and hopefully, first of all, detect that there is white mold in the field, but then also the challenge of how do you get an accurate treatment map when you're having to pay someone to walk and inspect the plants manually. So they've advanced their commercialization. This past year, I also became aware of the Center for Research on Programmable Plant Systems. That's based out of Cornell University in Ithaca, New York, but they have partners such as the University of Illinois. And they've highlighted this year that they've developed a variety of tomato that changes red at early nitrogen stress, and so can enable treatment to occur at an earlier stage than is currently the case. Last year, I mentioned compute as a limitation or constraint at the CES event in Las Vegas in January, both from AMD and also NVIDIA. There was a very subtle acknowledgement that we're reaching the limits of silicon scaling at roughly 1 to 1.5 nanometer feature size. And a lot of their presentation was focused on the increased performance coming from memory and I/O bandwidth. Quantum computing continues in development, and you keep hearing about greater numbers of qubits in the quantum computers, but haven't really had that breakthrough to what's called quantum supremacy, where quantum overtakes silicon. And then this morning I was reflecting also that, is there an opportunity here for optical computing to help with the breakthrough? So you've got that initial optical input into the system, and is there some processing that could be done optically before it gets handed off to either, well, probably to silicon for further processing? I added weeding robots. Rex has kind of highlighted why. It's a long-term problem that has only been growing. About 25, 30 years ago, glyphosate was introduced as the herbicide to end all herbicides. Funding and development projects for chemical herbicides were basically dropped or significantly reduced. And now we have this problem of the weeds that won't die with the existing chemicals. And it takes 10 years and $200 to $300 million to develop a new chemical. There's concerns about the environment. And so we're looking for something better. Rex was showing a number of the robotic technologies that are out there for weeding, particularly the mechanical and the chemical. I'll highlight laser treatment. So there has been some press lately with RFK Jr. talking about laser weeders and being able to reduce chemicals in farming. The challenge is the cost. And so for soybeans in North Dakota, weed treatment costs are $50 to $100 an acre. Profits are squished, so there isn't a lot of opportunity. And so if you can get a laser system to work, that would be great, but currently it's about $250 per acre. And so we need to get that reduced. We also need to get the speed up for commodity crops. And I see we're at 10:30, past 10:30 Central Time, so I'll turn it back to you, Helena.
Thank you so much. I mean, one of the things that Rex technology is actually good. The robotics I have been experienced myself when I visit North Dakota last year. But that picture of the 2 meters width, it just really blew my mind. I have to say it is like it's unbearable to me. But yeah, a lot of things are happening right now in the market. And I would like to thank you all. I mean, it's time for us to finish here. I would like to thank you to you all. There is different reasons to adopt the technology. This is something that we need to work with the farmers directly, but also with the companies that they are making the full integration systems that they are going to be deployed in the farm and into the food industry. So when to use RFID, when to use multispectral, when to use hyperspectral, when to use one or other spectroscopy method, when to use robotics, when to use autonomous. It will depend because this is a really difficult market. This is like very specific. So I'm really thank you to you all. Thank you for coming to this online meeting and participate here. Thank you to our speakers, Stravos, Lex, Michael, Rex, Stefan, and Noel. Thank you so much, Jose and Tulsi. And for the moment, this is farewell. I'll see you later. Thank you so much.
This is Optica. to